Alpha hydroxy acids are naturally occurring acids often used as cosmetics. The flowchart below shows some reactions of an alpha hydroxy acid with this formula in specific. And we need to fill in the boxes to show the organic products of reactions 1 and 2, clearly showing the relevant functional groups. So to clearly show our relevant functional groups, we either need to draw our structures as a structural formulae or displayed formulae, or a combination of the two as shown over here overall. So let's start by looking at reaction 1, start us off. So we've got our alpha hydroxy acid here, and we can see that we've got an alcohol functional group and a carboxylic acid functional group. So these are going to be the key groups which we're looking at to see if they react or not. So in reaction 1, we've got a carboxylic acid with some sulfuric acid, and all of this is being heated. And these are the reagents for our esterification reaction overall. And this means that we're going to get a reaction with the alcohol from our AHA and with the carboxylic acid from our reagents, and this is a sulfuric acid catalyst overall for this one. So let's draw out the structure of our product for this reaction. So we've got our carbon centre, and I'm going to start by drawing on the parts of our AHA which have stayed the same. So our acid has not reacted in this reaction. We've still got our carbon chain here. I'm just drawing it exactly the same as it was shown in the structural formulae to keep things easier and neater. And then now we're going to have our ester bond. So you can either draw this out in full displayed formula or structural formulae is also fine. So I'm going to draw it in structural formulae where we use the COO, the COO, to represent the ester bond, which looks like this overall. And that is our COO for the ester. So that was our reaction 1. Let's take a look at reaction 2 now. So for reaction 2, our reagents are sodium bromide with sulfuric acid again, and this is all being heated. And these are the reagents for a nucleophilic substitution reaction. So we're going to be substituting the alcohol from our AHA with a bromide ion from the sodium bromide. And this sulfuric acid is again acting as a catalyst to help substitute out the hydroxide with the bromide overall. So let's draw out the product for this reaction. So again, I'm just starting by drawing out the bits which have stayed the same, which have remained unreacted. So this includes the acid group and the carbon backbone. And now we've substituted out our alcohol with a bromide for this question. And in order to get the 2 marks, it's 1 mark for our first structure from reaction 1 and a mark from the structure from reaction 2 overall. Give the full systematic name for compound G, which is shown here below. So let's start by drawing out compound G in a more detailed display formula so that it's a little bit easier for us to name. So I'm going to start by drawing in the double bond. We've then got our carboxylic acid group, and let's add in our hydrogen here. Then we've got another hydrogen up here, and then an ethyl group overall. So we've drawn this out. So now what we want to do is we want to try and identify what our main functional groups are. So we've got an alkene here, and we've got a carboxylic acid. So we need to find the longest carbon chain, which includes all of these functional groups. So this one, we've got a 5 carbon chain overall. So therefore, we've got some form of pentanoic acid from this carboxylic acid bit, but because we've got an alkene, we've got to have some form of a pentenoic acid. So a pentenoic acid. And we need to specify exactly which carbons the alkene bond is between. So whenever we've got a carboxylic acid, because this functional group always has to be on the end of a carbon chain, we always label that as carbon number 1. So let's number the rest of the carbons in the chain. So we can see from this that our double bond is between carbons 2 and 3, so therefore we go the lowest number, and this is going to be pent-2-ene oic acid overall. And then the last thing to bear in mind is that when they've drawn it out in this crab structure here, we can see that across this double bond, we've got some EZ isomerism overall. So because of the double bond, we've got fixed displayed formulae here because we've got no rotation around that double bond. So it's fixed in space. So we need to look and see which are our high priority groups and whether they're on the same side or the different side of that double bond. And that's using our Kahn-Ingold-Prelog rules in order to identify whether we've got E or Z. So our highest priority group is going to be the acid group, and that's because we've got the carbon and then the oxygen is the next along, and that's got a higher atomic number than this second along carbon over here. So we've got, that is our first priority, this is our second priority, and these hydrogens are both of equal third and fourth priority there. And what we can see is our two highest priority groups are on opposite sides of that double bond. Therefore, we've got the E isomer. So just to finish off our name, we just put an E at the front. This can be in brackets or just written normally. And overall, our name is going to be E pent-2-ene oic acid to finish that off. Compound H is a stereoisomer of compound G, which is shown here to the right. And for this question, we need to suggest a structure for compound H and draw the repeat unit of the addition polymer that can be formed from compound H as well. So let's start with thinking about the structure of compound H. So we can see from the structure of compound G that our two highest priority groups are on opposite sides of the double bond. So we've got the E isomer for compound G. And we have the stereoisomers across this double bond due to them being fixed. So the double bond means that the bond is fixed, so it can no longer rotate freely like a single bond. Hence, the atoms are fixed in space in this configuration. So if we've got the E stereoisomer for compound G, then compound H must be the Z isomer. So we just need to flip one side of the double bond. So I'm going to flip this side on the right here. So we're just swapping those over so that our two highest priority groups are now going to be on the same side of that double bond overall. So just like this here. And there's our Z isomer for compound H. So now let's draw the addition polymer for this one. So in order to draw the repeat unit of the addition polymer from compound H, we can just imagine breaking one of these double bonds and it opening up to sort of form bonds onto the other sides of the carbon. So we're opening up this double bond to form bonds either side of the carbon so that this unit can then repeat down a chain. So let's have a go at drawing this out like so. So our same structure we had before, and then we're opening up that double bond to form bonds either side for this one. And we need to show these bonds in order to get the mark for this question. So there's one mark for the structure of compound H and one mark for the structure of this addition polymer, but we just need to make sure that we show these bonds, and that's just to show that this unit is repeating along the chain. And we could draw brackets and put an N outside the brackets if you'd like, but in this question you don't get any marks for it because we've already identified that we've got the repeat unit overall. We are then told that the addition polymer from above is used widely in industry overall, and increasingly waste polymers are being processed as a more sustainable option than disposal. So they're processing them instead of just throwing them away. And we need to identify 2 methods for usefully processing waste polymers that does not include recycling overall. So because we've got an organic hydrocarbon-based compound, and we know that when we burn hydrocarbons, when we combust them, we get a lot of energy because there's a lot of energy stored within these bonds. So one way which we could usefully process waste polymers could be the combustion of them for energy production. And we need to make it very clear that we're combusting them for the production of energy. So we're actually using the energy from this combustion rather than just saying burn the polymer. So we need to make it clear why we want to burn that polymer to link it into the question where we're usefully processing them. So that's one method. And another method could be as the use as an organic feedstock overall for the production of plastics or other organic chemicals. So the production of plastics or some other organic-based chemicals. So what this means is that we could use our waste polymer as a starting point. So sort of like the food to make the plastics and all other organic chemicals there. So as the starting point overall, instead of just throwing them away. And for this question, it's 1 mark for each method. A student synthesizes a sample of the alpha hydroxy amino acid J, shown below, using this reaction scheme, and we're starting from propane 1,2-diol. So in this reaction scheme, we've got 2 different steps to go all the way from propane 1,2-diol to our alpha hydroxy amino acid J. And for this question, we need to state a suitable oxidizing agent for step 1. We need to write an equation for step 1, and we need to outline the mechanism for step 2, making sure that we show our curly arrows and any relevant dipoles in the mechanism. So for step 1, we're oxidizing our diol and we're producing a compound which contains a carboxylic acid and a ketone here. Therefore, our suitable oxidizing agent is going to be our acidified potassium dichromate. So acidified, and we could use, for example, some sulfuric acid to do that. And then we need our potassium dichromate, which has this formula here. And our equation for step 1, we need to draw out the structure of propane 1,2-diol just to make that clear why that oxidation is occurring and to make it consistent for our equation. So I'm going to do this in skeletal formula to keep it consistent with the product that's being supplied for this question. So we've got propane, so we've got 3 carbons in our backbone, and then we've got an alcohol group on carbon number 1 and on carbon number 2 there. And for our product, we've formed a compound which has got a carboxylic acid on the end and a ketone on carbon number 2. And this is because when we've oxidized our propane 1,2-diol, we've oxidized a primary alcohol fully to this carboxylic acid, and our secondary alcohol has been oxidized to this ketone here. So therefore, for our oxidizing agent, which we're representing using square brackets with an oxygen in the middle, we're going to need 3 equivalents. So we need 1 equivalent to go from the secondary alcohol to that ketone, and then we need 2 to go all the way from the primary alcohol to the carboxylic acid, because if you oxidize your primary alcohol, you first go to the aldehyde and then you get to that carboxylic acid. So there's 2 levels of oxidation there, hence we need 2 equivalents of that oxidizing agent. And for each alcohol you oxidize, you produce a molecule of water as well. So in total, we've produced 2 molecules of water. And you could also check this by counting up your atoms and making sure that you've got the right number of oxygens, hydrogens, and carbons in total. So we've done these 2 parts here. So now we're going to have a go at outlining our mechanism for step 2. overall. So for step 2, we're going from our carbonyl-based compound to our alpha-hydroxy amino acid compound J. And we're using our sodium tetrahydridoborane, which is a strong reducing agent overall. So the first thing to note is that this is going to be a reduction reaction. And as we can see from the difference in our structures, we're going to be reducing this ketone back to a secondary alcohol overall. And this is the reagent which we use to reduce carbonyls, so to reduce aldehydes and ketones. And that's because it's a source of hydride ions. So let's have a go at drawing out this mechanism. So I'm going to start by drawing out our carbonyl compound, like so. And then I'm going to add in a dipole into our carbonyl bond. And this is going to show exactly why this hydride ion is going to want to attack this carbon centre. It's because it's slightly positive due to the polar bond. So our first arrow is going to be from that hydride, from that negative charge on the hydride, so that represents the electron source, so we've represented that we're flowing those electrons to that slightly positive carbon centre. And then this causes one of the bonds between the carbon and the oxygen to break, and a pair of electrons to flow onto that oxygen. So then our intermediate is going to look like this. We've still got our carboxylic acid, and now we've got a negatively charged oxygen because we moved 2 electrons onto that slightly negative oxygen, forming this full-on negative ion. We also added in a hydrogen, but because we're drawing this in skeletal formula, to simplify things, we don't need to show that hydrogen here, but you could draw it out in full displayed formula if you'd like, showing that hydrogen. And now we have a reaction with our acid. So this is the second step of our reaction, where our negative oxygen is going to be attracted to the positive proton. And now we've formed our compound J, our alpha hydroxy amino acid overall. So we've added on a hydrogen and we've reduced our carbonyl down to a secondary alcohol. And for notes, this was a nucleophilic addition reaction. So it's a nucleophilic addition mechanism for our reduction reaction. And for this question, there is 1 mark for identifying the oxidizing agent for step 1. There's 1 mark for writing the equation for step 1. And then there's a mark for drawing the curly arrow from that hydrogen hydride ion to that slightly positive carbon centre in our mechanism for step 2. And then there's a mark for drawing the curly arrow from one of the double bonds to that oxygen, but we also have to have that dipole there in order to get this mark. So there's the bond for the second arrow, and it's also for that dipole. So you have to have both of those bits in order to get that 4th mark. And then the final mark is for drawing our intermediate and the arrow from that negatively charged oxygen to our positive hydrogen ion there. And that's how we get the 5 marks for this question. The reagent used in step 2 of the synthesis, shown below, was sodium tetrahydridoborane, and this compound contains the following ions shown here. And for this question, we need to draw a dot and cross diagram of our sodium tetrahydridoborane and give the full electron configuration of our 1+ sodium ion. And we only need to show the outer shells of electrons for this question. So let's start by thinking about the full electronic configuration of our sodium 1+ ion. So if you look in your periodic table, you can see that sodium has got 11 electrons as a neutral atom. Therefore, the electronic configuration of the neutral atom will be 1s2, 2s2, 2p6, 3s1. So there's our outer shell electron. We've got just 1 because it's in group 1 of the periodic table, and it's in the s block because the outer shell electron is in an s orbital. So when we lose this electron to form a 1+ ion, our electronic configuration is going to be 1s2, 2s2, 2p6 only. And this electron is going to be given to the boron to form that negative ion there, because we've got an ionic bond to think about. So let's draw the rest of our dot and cross diagram now. So we've got our boron, and boron is in group 3 of the periodic table. So that means that it's got 3 electrons in its outer shell. And this is going to form covalent bonds with 3 hydrogen atoms, like so. And then we've got the electron which the sodium has donated. So there's an electron transfer from the sodium to the boron in order to form this ionic bond. And therefore we can form a 4th covalent bond now with another hydrogen, and we've got our negative ion here. And for this question, there was 1 mark for our dot and cross diagram, but we need to be careful here because in order to get the mark, you've got to use different elements to show where each of these electrons have come from. So on my diagram, I've used crosses to represent electrons from the hydrogen, dots to represent electrons from the boron, and then just a circular outline to represent the electron from that sodium there. And then our second mark is for the full electronic configuration of the sodium 1+ ion. And to get that, we need to draw it out in full, as I've shown, not using any abbreviations with noble gases or helium. Compound K is an alpha hydroxy amino acid that is often used in chemical face peels. A student wishes to identify compound K from this list of compounds below. So we've got glycolic acid, malic acid, mandelic acid, and pantoic acid. The student isolates compound K and analyses a sample of the compound via titration. And here's the method for our titration here with our key values. So the student dissolves 1.89 grams of compound K in water and makes the solution up to 250 centimetres cubed in a volumetric flask. The student then titrates 25 centimetres cubed of this solution with 0.150 moles per decimeters cubed of aqueous sodium hydroxide. And we are told that 18.8 centimetres cubed of sodium hydroxide was required for complete neutralisation. So we need to use these results in order to identify compound K from this list above, and we need to show all of our working here. So we need to show all of the different steps overall. So let's start by working out some moles. So we've been given quite a lot of information, so we need to find a suitable starting point. So in order to identify compound K, we're going to need to have a molar mass overall. So we need to work our way back to get that molar mass of K. So the first thing which we can do is work out the moles of our sodium hydroxide that have been used in the titration overall, because we've got our volume and we've got our concentration. So the moles of sodium hydroxide is equal to the volume times by concentration. So we just need to make sure that we divide our volume by 1,000, and that's so that we're converting it into decimeters cubed, which is the appropriate unit because that matches up with the concentration units. This multiplied by 0.15, and this gives us a moles of 0.00282 overall. So now we need to use this to work out the moles of the acid that we've got. So each of these compounds are alpha hydroxy amino acids, so we can see that they've all got a carboxylic acid group in them. And we can see that from this list, we've got 3 monoprotic acids and 1 diprotic acid. So because the majority of these are monoprotic, it would be a sensible assumption to assume that we've got a 1-to-1 ratio overall. So for now, we're going to assume that our ratio of the acids to the sodium hydroxide is 1 to 1. Therefore, our moles of the acid in the 25 centimetres cubed, because that was what was used with the titration, is going to be also 0.00282 moles overall. So now we've worked out how many moles of acid we've got from the 25 centimetres cubed, so we need to use this now to work out how many moles of acid we had in our 250 centimetres cubed. So we're working our way back to that original solution which was made up. So we're going from 25 centimetres cubed to 250 centimetres cubed, and to go from 25 to 250 you multiply by 10. Therefore, we also need to multiply our moles by 10 overall. So our moles in 250 centimetres cubed is going to be 0.0282 moles. So now we can work out the molar mass of K, because we've got the mass which we dissolved into the solution, that's 1.89, and we've got the moles from our 250 centimetres cubed solution. So that's mass over moles there, so we've got 1.89 grams divided by 0.0282 moles, and this gives us a molar mass of 67.0 grams per mole. So what we want to work out is if this matches up with any of our acids from the list. So because we've got quite a low molecular mass, I'm going to start by seeing if this matches up with the smallest acid that we've got. So that's glycolic acid here. So our molar mass of glycolic acid, if we work our way along, is going to be 1 from the hydrogen there, plus 16, plus 12, plus 2, plus 12, plus 2 lots of 16, and plus another 1. And this is going to give us a value of 76 grams per mole. Now this is greater than our value that we calculated for our molecular mass. And glycolic acid is the smallest acid out of each of the monoprotic acids. So this tells us that we must have a diprotic acid. So we must have a slightly different ratio of our acid to our sodium hydroxide. So therefore our acid must be diprotic, and this will therefore affect our ratio, because now instead of having a 1-to-1 ratio of our acid to our sodium hydroxide, we now have a 2-to-1 ratio instead. Therefore, our moles of the acid will be halved in total, which means that we can double our MR. So we can times this by 2, and you can work this all the way through as well, and this gives us 134 grams per mole. Now we've only got one diprotic acid from the list, so our answer must be malic acid, and as you calculate the molar mass of malic acid, this is also 134 grams per mole. So we've got two different ways of checking that our answer was correct. And for this question, there was 1 mark for working out the moles of sodium hydroxide using that titration. And then the second mark was for working out the moles of the acid in 25 centimetres cubed and the moles of the acid in 250 centimetres cubed. So you had to have both of these points in order to get that second mark. Then the third mark was for working out the initial molar mass of K. Then, as we deduced, we figured out that K would have to be diprotic, so the fourth mark is for some statement in there which identifies that none of the molar masses of the monoprotic acid linked up with our answer, therefore we must have the diprotic acid. And then the fifth and final mark was for therefore identifying that K must be malic acid.